So now, let me introduce you to Luis Lavena.
Hello, everybody. So tough spot being after lunch. Everybody will want to have a nap. So we should talk a bit about Ruby and Crystal. So Crystal programming language. Oh, sorry. What's going on? No, don't worry, don't worry. It was just me having on the wrong screen. There you go. So my name is Luis Lavena. You can find me on Twitter, rant, say whatever you want. And on GitHub, you can find with that username all the stupid things that I upload. So to have a little bit about my background, I'm a creator of Ruby installer for Windows. So anyone that has suffered at some point working with Ruby on Windows, that's my fault. And nowadays, I'm retired, but after 10 years, I think I did some good. I think the community grows so much, and nowadays it runs, so that's good. I'm also a Ruby core committer, so I'm not as hard as Nobu or anybody else, but some of commits associated with Ruby for Windows are connected with the work that we did on Ruby installer. I work for a company called Area 17, Area 17. We're a digital product agency. They sponsor my trip here. I actually moved to France, so I'm an expat Argentinian moving to France. And I wanted to thank them for having me here. And now this is a technical talk. So before we jump into the deep technical stuff, I wanted to give you a warning. This is something really important. So you know I'm from Argentina. So tomorrow is French match. And now that I'm an expat, make things very difficult. So this is a warning. So let's talk a little bit more serious. Let's talk about what are like Crystal, what is Ruby, like how that works, things in relation to compiled languages versus interpreted languages. So there are differences between those two. So we're going to focus it on the aspect of the compiled languages and how that refers and generates machine code and what that means and what the computer is doing when also talking about interpreted languages. So let's take a look about how Ruby works. Ruby starts from the require, and it reads the source code. Then it converts that into tokens that represents your code. Then it parses and builds what's called an abstract syntax tree. From there, it builds what's called an instruction sequence. An instruction sequence is what tells the virtual machine how the code works. And then it executes that instruction machine. So that instruction sequence is run inside the virtual machine, nowadays called YARV, which is yet another Ruby virtual machine, and from Ruby 1.9 up to newer versions. Now, this is how the process of Ruby works. Now, how that compares to a compile language. A compile language is quite similar. A compile language reads the source code, tokenizes, parses through a lexer, but now instead of building an instruction sequence, it's going to code-gen. It generates code that is going to work for that native machine. It's going to compile that native code, and then it's going to link, collect all those objects, and generate a final executable that's going to run natively on your operating system. Now, that happens on your operating system, but depending on the complexity of the compilers, you're going to find that there's like a phase between the parser and the code gen that's going to analyze your code, do some type checking, do some optimization. So LLVM, most of the languages based on LLVM, for example, they're going to do optimizations outside of that, and LLVM is going to do also optimizations. So this is kind of like an overlook. But now, the funny part, the most interesting part happens on that part, the analyze, the infer, optimize, or as I wanted to call it, magic. So the magic behind that, it's a little bit interesting. So let's take a look to that. And let's take a look at one concrete example, which is Crystal. Crystal language has all those similar phases as we talk about a compile language, but then it has other things. It's been inspired by Ruby, so it has a syntax similar to Ruby. It can bind directly to C libraries. It doesn't need to have like a custom extension API, so you can write directly natively on on Crystal. You can also have things that you don't have dynamic typing. Not dynamic typing. Apologize. You don't have like meta programming techniques like you can see on Ruby, but what you have is macros. Macros are automatic code expansions that are even more powerful than meta programming in some of the cases, because what you generate then it goes to the compiler, it analyzes what you generated, and at compile time you can know if that's going to work or not, and not wait for your test to pass. So the syntax is similar. It generates a native executable, single file executable on your machine. It's powered by LLVM, so similar to Rust, similar to other language implementations. And the cool thing about that is we're going to focus on one specific part, which is types and inference. So let's talk about that single point. Type and inference means what you have, like, for example, you have an integer, you have a float, you have a number, a string, a single character, you have any type of representation that represents that data on your program or represents an object or instance of an object, things like that. It's a type. And then inference means things are going to be inferred that you're not declared. So who's familiar with C language? Cool. So on C language, if you don't define the type of something, C compiler is going to complain. It's going to tell you that's not going to work. And you need to tell what is the type. So on infer language, it's the opposite. An infer language is going to guess the type based on the information that you provide, the context. So as it parses the code, it analyzes the code, it's going to say, OK, A, it's actually an array of numbers. So I can check what is A, the values, and I can check the type. So it says it's an array of type int32. And then I can define B as an array that contains a number, a string, and a character. And you can see here on the signature that tells it's an array that contains either a string, an int, or a char character. And when you try to add something that is not one of those things, a compile language like Crystal is going to complain and tell you, like, yeah, I didn't expect that you tried to add a float to this, and the type doesn't match, so you need to tell me more information. And all those things happen at compile time. It happens way before you actually run the code, way before you actually run the test. So having that information up front is really helpful to help you write better code. So another example of that happens with methods and method inference. So you can define a method, like in this case, a simple one. You add 1 and 2, and that 1 and 2 can be numbers, can be strings, or can be, in this case, trying to add a string and a character together, and that's not going to work because the string is not supposed to be concatenated with a character. Now, and you're going to get that error at compile time. So the same thing happens when you try to invoke methods that are defined on things that are not there. So in this example, you can see that I'm trying to call the work method with a worker new that's going to compile, but when I pass a nil value, it's going to say that there is no method something on nil. And from Ruby, you are familiar with that error, like undefined method something for nil. In this case, this happens at compile time. I didn't run my program. I just check it, and it tells me from the get-go that it has an error. Similar thing happens now when I added a fence or a workaround to this to say, like, if I have a worker, do this. So by adding this technique, I can say, like, only when worker is a valid value or valid information, run this which is worker.something. So in this case, I call the worker if it works. I call worker nil, and it fails. Well, sorry, not fails, but does nothing. Now, I can limit this into forcing with method signatures. So instead of relying on inference to let the compiler to figure it out, the types and everything, I can tell, OK, this is my method, and my method only takes integers. And when I have those integers, doesn't accept anything else. So when I do this, and I try to compile now with something else, it's going to fail. But it's going to fail differently, because I already have the signature of the method. It's going to fail even faster, because the compiler doesn't need to do all that guessing that you try to do. And that's great. Now, that's an advantage of a compile language that Ruby doesn't have. And on current explorations, there's been a lot of attempts to try to do this with Ruby, some successful, some papers at the university, and some just vaporware. So Ruby type syntax will be hard to implement. That's what I got it from the last couple of meetings and presentations from Ruby Kaiji. It's really hard to implement. Most likely, it's going to come in the form of interface signatures, meaning that if a duck quacks, then is that instead of types. So it's going to look for that signature. And there are other attempts to do something similar outside of the language, which is in the case of Sorbet from Stripe is trying to do that kind of exploration, trying to have a type checker that you can run all the time that parses your code, analyzes what you're doing, and tells you, like, yeah, there is a potential for this to not work. And you can get those errors before running your program. So that's a plus for someone developing. Now, let's talk about code techniques. I show you a couple of just a quick detail on like how to work around that potential nil value on Crystal. And I just wanted to start with this, like, nil is your friend, really. So you need to learn that the chances of nil happen on you are really high. So you should not program to, like, this is never going to fail, because you know that's not true. So consider nil and one of the possibilities and work around, like, and code around that scenario. And once you start doing it, when you're testing a compile language and you're doing those techniques, once you get back to Ruby, it's more easy to detect those type of things. And it's like, oh, no, there's a potential for this to be an empty thing, or there's a potential for this not to be a string that I was expecting. So once you start doing those type of things, once you acknowledge that, it makes more easy for you to write code. So in this case, it's similar. And the problem is, like, on this case, on Ruby, fails at runtime. So you can do the exact same thing I did on Crystal and work around that scenario, and it works. Now, that's fine. The other challenge is accessing variables across threads. Now, we know Ruby is a single-thread language. It has a global lock that avoids you modifying things across things, but that doesn't mean that another thread, when it was suspended, modifies the value that you're trying to access. By meaning that, let's take this example. I have a worker that has a method work, and I base my call on this method based on a condition that comes from an instance variable. But that instance variable might be changed from another thread, might be changing through other, like a callback or things like that I have hooked up in the system differently and got into this instance of the worker and tries to do something with that. And condition now is not the same thing as was before. One of the recommendations that to avoid that, to the potential scenario of condition being nil, or condition being something that is not what you're supposed to do, you can do is capture that into a local variable. And might sound expensive, but at the same time, you guarantee that that value that you capture is the right value at that time. So if that if was more a complex condition, saying this condition is actually a type of query or things like that, an instance of any type of objects, you guarantee that if you only get into that branch of code, if that condition pass. So by doing that, you guarantee that value is what you expected on your code. And it's like, oh my God, it's too much code. But at the same time, you're just saving a potential runtime error, like why it fails 1 of 10 times. So we already have those two things: acknowledge that nil exists and accessing variables across threads. So those are code techniques that you can take from compile languages. But there's more techniques that you can take from compile languages. One of those, I call it, sorry, this is the Sorbet type checking link. So anyone that can go take a look to that. They hasn't been released to the world from Stripe, so still vaporware kind of thing. But let's talk about optimization techniques. The other aspect of this is what you can learn from a compile language, how you can improve your environment and how you can improve the things that you do by relying on how the others do those things. So one of those aspects is load time. And we know by working with Rails applications that load times takes a lot. And booting your application either locally on the servers is not instant, it takes a lot of seconds. And when you're deploying, you need to use techniques like rolling deploys just to make sure the right server with the right version has the right thing while you're deploying, things like that. Really complicated. We start creating tools to solve things that comes with the language, that comes as problems with the language. Boot time is one of those things. So you remember the chart that I showed to you, the require process and everything until an instruction is loaded? And this is how it works. Now, you have the I/O aspect where it reads the file. So for every require that you do on a project, even the calling the same file like Ruby and run the file name, it goes through this process. So you read the file, and then it tokenizes, uses memory for that. It builds the AST, builds the instruction sequence all in memory, and then it executes that instruction sequence on the virtual machine. So all that process needs to happen for every single file. So if you have a project that has 10,000 files because you're using Rails, then it will depend on the speed of your hard drive, is a solid state or not. It will depend on the type of file system. It will depend on a bunch of variables that will make your loading time of the application variable. So what if I tell you, So this is how the instruction sequence works. So what I did here is take an example code, a file that has a local variable, an input. And then what I do here is write into a file, a binary file, write this instruction sequence, the compilation of that sample file that I did. And it generates a file that is the binary specific for the platform that I generated that. And then when I run it, I loaded that file and run it directly into the VM using eval. It's not the eval that you know, but it's directly the eval for instruction sequence. I get the results. So what if I tell you that there is a way for us to bypass some of these elements and be able to have close to a binary type of thing that avoids that loading, that I/O, and that avoids that generation time that takes parsing files and everything? So imagine that I read bytecode, the slide that I showed you before, and then I send it directly to the virtual machine, right? Doesn't sound complicated. Well, starting from Ruby 2.3, that is possible. And that is actually something that Bootsnap is taking as an approach. So Bootsnap is a gem that you can use on your Ruby on Rails projects. It figures out all the files that you need to load. It compiles in bytecode all those things and keeps tracks of the files that you load. And then it optimizes the load path. So when you do a require of that file that's already been compiled, it just do an op. It doesn't do anything because it's already been loaded. And when it does, it loads the bytecode. And when the bytecode doesn't exist, it loads the file, compiles the file, generates the bytecode, and then it loads it. So it does all those things for you. And the amazing things, this is not snake oil, but you can get around a 35% of performance win on boot time of an application by introducing Bootsnap on your boot process. So on the README has better numbers. It will depend on the size of the application. It will depend if you're loading a C extension. It will depend if you're doing any type of operation when the application boots that is connected with the database, things like that. But overall, you can get around a 30% of boot time optimization by introducing that and by using bytecode. So you're one step ahead into a compiled land. Welcome. So that's load time. The next one is installation time and dependencies. So, and I'm going to show you this without any introduction. How many of you are familiar with this? Raise your hand. Good. So you know what this means. So, and this is kind of like, it can go as a week sprint, updating all the projects that depends on Nokohiri to actually get the latest version. And the problem is with this is that compiling Nokohiri, it's something that takes time, right? So you think it's like just gem update or like bundle update and you get the new version. No, you're actually compiling code because within Nokohiri there is libxml, which is the library that does the actual XML parsing, and it needs to be compiled into a native code that the computer runs because it's a C library. And all those type of things happens every time that you do gem install or that you do bundle install and those type of things. And that process needs to happen on your dev machine, on your CI, on your staging environment or your production environment. It will depend on how you're sending that information to the server, to the final server. So we're not talking about just that, just the amount of time and power that it takes to compile Nokohiri every single time, but we're also talking about bandwidth. Nokohiri gem weighs 8 megabytes. Every time that you need to do that, and if you multiply that by multiple servers doing the traditional Capistrano deploy, you're downloading that gem N or X amount of times. You're compiling that, so wasting a lot of resources compiling that every single time for every deployment. So what if there is an alternative to that process? What if it's like you don't need to waste those resources every single time? So let me introduce you to a technique. You will see here, like installed Nokohiri on my local computer. It's an i7, so most likely more powerful than an EC2 instance. It took me 5 minutes. I compile the gem, most likely will get me for other 5 minutes, but when I try to install the binary of that, it took me 5 seconds. And the binary of that gem is way smaller. So let's talk about Gem Compiler. It's a Ruby Gems plugin, so you can invoke it with Gem Compile. Pre-compile gems for the current platform, so if I'm on Linux, I can pre-compile extensions and use those. So you can precompile Puma, Nokohiri, any type of C extension. It's friendly. It plays nice with bundle package and bundle install local, meaning that if you decided to bundle the gems with your repository so you can work offline, so you don't need to depend on Ruby gems being up or down or whatever type of situation is happening in the world, you can have that on the cache. You can compile it, and then you can install it locally. And it's going to work, and it's going to work fast. Not only reduce the installation time, but also reduce the bandwidth. So you no longer need to download 8 megs of Nokohiri. You only need to download 700K. That is the compiled version. So there's a big win there that you can use nowadays. It's a gem. Just look up for Gem Compiler. Disclaimer alert: I'm the author. So. But something that I don't say here is that you not only save bandwidth, save the world, kind of thing, but you also are ensuring that your dependencies are with your code. And you don't need Ruby gems and things like that. So now we have load time, installation time, and dependencies. So the time that you wasted compiling once, you don't need to waste it, or nobody else needs to wait for that particular version. You can just use that version every single time that you install any new server. And let's move to the third point of optimization techniques. And this is an interesting point. So I'm just going to quote it as anonymous and paraphrase this, but you can read it for yourself. This is an excellent, this is sarcasm mode on. This is an excellent PR. Even the inconsistency style and spaces used for your hashes, the lack of parentheses and methods, and let's not forget the usage of tabs. This is true. Summary of a full rant happening on GitHub, but this is happening to a newcomer. This is happening to someone that wants to contribute to your project. This is something that wants to work with you. Maybe upgrading documentation or maybe improving your gem. And if you're an open source contributor and people send something that doesn't look the way you want, this is kind of like the code becomes an art. And art is a very subjective thing. Like, I will do hashes one way. You will do hashes another way. Somebody else will decide to use 4 spaces instead of 2, and those type of things. And because Ruby is flexible, Ruby aspires to make your life happy, to make your life better. It will not enforce those things on you. But there is a downside of that. And the downside is that those things, like I showed you before, happen. So what about introducing formatting code? Formatting code has a lot of advantage. It reduces the endless discussion around the style and let you focus it on functionalities. Like, OK, that method does the right thing. I don't care if you use spaces or tabs or whatever. Like, you just follow the style. So it's clear that having a unified style and applying that consistently helps. So let's take a look, for example, to languages like Go, Rust, recently Elixir, and there's a bunch of other languages that are start introducing that because it works. Because it lets you reduce waste of time, human time, and let the machine do it, and really focus on things that matter. So there is a gem for that. It's called Rufo. It's actually was originally created by the creator of Crystal. And by the way, Crystal has a formatter. So similar to Go and everything, it formats your code, following their coding style. So this is Rufo, Ruby formatter. It applies the recommendations of the Ruby style guides. It formats your code accordingly. It has some flexibilities and some tweaks that you can apply to it that makes you, say, for example, if you wanted to align constants or if you wanted to align equal signs and things like that. So even more, you can use it as a check on your CI environment. So every time that someone sends you a pull request, you can run this just to check that. And like, I'm not going to look at the code because I'm not going to waste time on the formatting. I want to focus on the feature. So by using this type of techniques, you stop worrying like how, like, I don't like that space, or I don't like, let's use rocket hashes, or let's use symbol hashes, things like that. It doesn't matter anymore. So now we have those 3 type of things. With those 3 type of things, we can create better code. Those are learnings that we can take from a compile land that we can apply to our Ruby code every single day. We can apply it to a company. We can successfully apply to our open source project and stop worrying about being unpolite to newcomers that sends contributions to you because you don't like the coding style. Or if you have a really slow Rails application to boot it up, you can just use techniques that improve that performance. So those type of techniques you can take from compile land, that you can take from learnings of using a compile language, distributing binaries that you don't need to care about, like what gem to install or how long it's going to take. You can take, OK, I can speed that up. I no longer need a compiler on the server because I already have everything compiled. So those type of things, if you start adding those things into your tool belt, you put it as part of the things that you do or part of your workflow, you're going to be able to spend time doing something else, creating new things, or being able just to be out. It's a beautiful day outside. So I just wanted to give you that idea. These are the links. So improving load time, Bootstrap from Shopify, precompiled gem extensions from myself, and the code formatting from Rufo over there. So So I just want to give you that, and I want to say thank you to you.
Thank you, Luis. Okay, for one question.
One question. You can find me outside if you need something.
Hi, thank you for
Hi.
your talk. I have a question about the optimization. Actually, I learned a lot from interpreted language and compiled language, so thank you. What if I want to optimize, for example, my deployment, and I want to compile all my gem before install it? What would be the drawback? Why aren't everybody doing that? Is everybody doing that?
That's actually a very good question. The drawback is nowadays, I can spot it from all the Apple's lighting here that you have a Mac. And most likely you will have a Linux box where you deploy your application. So you will not locally compile on your Mac and then send that to the server because it's not going to work. So its native code works on the native machine. It assumes things about the operating system and things like that. But there are two approaches to that. Either you go into the server or have a virtual machine similar to that precompiles things for that, or stay tuned because there's like a service coming for that. Sorry, I had to do it. But you can also improve the development workflow by precompiling things for Mac. So if everybody's going to use the same Mac, you can have the source code, the original gem, you can have the precompiler for Mac and the precompiler for the server. And Bundler is going to automatically detect that and it's going to use the right one for the platform. So when you deploy to the server, it's going to use the Linux one. And when you deploy to, when you set up the environment locally, it's going to use the Mac version. And you are saving your partner's time working on that. Cool. OK? Anyone? No? You can find me later if you have any question. Thank you.
Thank you very much.